Okay, this is where we are now going to continue with the hyperbolic functions. And feel free to take advantage of the fact that you can stop me at any time to ask a question if you have one, right? So what we are going to deal with today is the hyperbolic functions. And then the starting point of talking about hyperbolic functions is by definition of the hyperbolic sine function, which is going to be indicated as a sinh of x. And then we define it as half is equal to e to the exponent x minus e to the exponent minus x. This is the definition. And then we are also going to define a hyperbolic cosine function, cos of x, as cos of x is equal to half into e to the exponent x plus e to the exponent minus x. And then all other hyperbolic functions will follow the normal trigonometric counterparts. Like for instance, the hyperbolic tangent is always going to be written as hyperbolic sine over hyperbolic cosine. And then if you have to define it in terms of those exponents, let me just get the pointer. And then if you are going to define it in terms of the exponents, then this is what the hyperbolic tangent is going to look like, because the halves will cancel out. It will be e to the exponent x minus e to the exponent negative x over this. And then hyperbolic cotangent, it will be hyperbolic cos over hyperbolic sine. The same way as cotangent is cos over sine, you see. And then hyperbolic cosecant is going to be 1 over hyperbolic sine, and so on. Now, if we want to use a calculator for the purpose of identifying the hyperbolic functions, like let's say for argument's sake, we want to work out hyperbolic cos of 0. And then in looking at the definition of hyperbolic cos, it means we are simply going to put 0 where we see x. So it will be half e to the exponent 0 plus e to the exponent negative 0. And we know that e to the exponent 0 is 1, and e to the exponent negative 0 is the same as 1 over e to the exponent 0, which is still 1. And 1 plus 1, if you divide it by 2, you get 1. Now, if you want to use the calculator for the purpose of identifying the same thing, you are going to key in, you should be having a button that is written HYP. You press HYP and you press cos. And then on the screen, you'll see cos to show that now we have arrived at the hyperbolic cosine. And then you then press 0 because you want the cos of 0. And then once you press equal, it is going to indicate 1 as the answer. We can take another example. If we talk about the hyperbolic sine of 0,5, for instance, then you are going to use this equation of the hyperbolic sine. And that's where you are going to put 0 in the place of x. I mean, you are going to put 0,5 in this case in the place of x. And if you use your calculator, it will be half into e to the exponent 0,5 minus e to the exponent negative 0,5. If you use your calculator, this is the answer that you get. But again, if you want to use the buttons on your calculator, you follow the same principle. You press hype and wherever it is, and then sine, and then 0,5. Then it will indicate to you that it's working out hyperbolic sine of 0,5. And then once you say equal to, it is going to give you the same answer as the answer that you had there when you work this out manually. So that is basically how we can use the calculator for the purpose of evaluating the hyperbolic functions. You'll stop me if there's anything that you'd like me to clarify. Now, we have what we call hyperbolic identities. The hyperbolic identities, they can always be as the Osborne's rule. And then if the trigonometric identity is the one that says cos squared plus sine squared is equal to 1. According to Osborne's rule, whenever there is a direct or implied product of sines, in other words, wherever in the trigonometric identity there is a direct or implied product of sines, then you change the sign to get the hyperbolic counterpart. Like for instance, in the case of the first equation, cos squared x plus sine squared x. Here, there is a product of sines. There is the product of two sines because sine squared is sine of x times sine of x. So to get the hyperbolic counterpart, it will be cos squared x minus, wherever there is a product of sines, you are going to put minus, and you are going to change the sign. If it was plus, you change it to minus. So the hyperbolic identity, that is the counterpart of cos squared x plus sine squared x is equal to 1, will be cos squared x minus sine squared x is equal to 1. Another example, we know that the trigonometric identity 1 plus tan squared x is equal to secant squared x. That's what we know from trigonometry. But when you look at tangent itself, it is sine over cos. So which means once we talk about tan squared, there is a product of two signs there, because it will be sine squared x over cos squared x. And then now, because there is a product of sign, that sign is going to change here. And then the hyperbolic counterpart is going to be 1 minus hyperbolic tangent of x is equal to hyperbolic secant squared of x. Another example, if you have cos of 2x is equal to cos squared x minus sine squared x, which is the thing that we are familiar with, the double angle equation from trigonometry. Here, there is a implied product of, there is a direct product of two signs. So to get the hyperbolic counterpart, you are going to say cos of 2x will be equal to cos squared of x plus, because now there is a product of two signs, and then it will be plus sine squared of x. Another example, a sine of 2x is equal to 2 sine x cos x. That is the normal trigonometric identity that we are used to. But when you look on both the left and the right, there is no product of two signs. That's why that one is going to just remain as it is. So it is going to be sine of 2x will be equal to 2 sine of x cos of x. It is going to follow the same pattern as the trigonometric one, for as long as there is no product of two signs. Another example, we know that cosecant squared of x is equal to 1 plus cot squared of x. But we know that cosecant squared is 1 over sine. Cosecant is 1 over sine. So it will be 1 over sine squared. So there will be an implied product of sines here. That's why the sign is going to change to cosecant squared, to minus cosecant squared. And when it comes to cot squared, we know that cot is cos over sine. So cot squared is going to be cos squared over sine squared. There's also going to be the product of two sines here. That's why the sign is going to change. And then you can rearrange this to say, okay, it means that hyperbolic cotangent is equal to 1 plus a hyperbolic, the square of, the square of hyperbolic cotangent will be 1 plus the square of hyperbolic cosecant. Another example, we know that sine squared of x is equal to 1 over 2 into 1 minus cos 2x. So to get the hyperbolic counterpart, because sine squared involves the product of two sines, there is going to be a change in sign immediately there, but the other things are going to remain the same. And then if you want to make sine squared the subject of the formula, then it means it will be this will interchange. And the last example, we also know that cos squared of x is equal to half into 1 plus cos of 2x. When you look at all the terms involved in this equation, you find that there is no product of two sines. Yes, there is a product of two cosines, but the rule only focuses on the product of two sines. That's why the equation is not going to change when you convert it to the hyperbolic counterpart. It's going to be cos squared is equal to half into 1 plus cos of 2x. So that is basically how we can derive the hyperbolic identities from the trigonometric identities that we are familiar with already. Right. Now, how do we determine the derivative of the hyperbolic sign? We are simply going to look at the definition of hyperbolic of sine. We know that the derivative will be the derivative of half into e to the exponent x minus e to the exponent negative x. So you can take the half out, and then the derivative of e to the exponent x is e to the exponent x. The derivative of e to the exponent negative x, it will be positive e to the exponent x, because this negative is going to multiply that other negative, and then but then this is the definition of hyperbolic cosine. So in other words, the derivative of hyperbolic sine is hyperbolic cosine, which is not very different from what we know from trigonometry, that the derivative of sine is cos. What about if it is now the derivative of cos? Again, we can use the definition of the derivative of cos, and it will be half into e to the exponent x plus e to the exponent minus x. And then if you differentiate this, you can take half out. The derivative of e to the exponent x will be e to the exponent x. And the derivative of e to the exponent negative x, it will be e to the exponent negative x times the derivative of the exponent, which is negative 1. That's why we are going to have negative here. But this is the definition of sine. So in other words, we can say the derivative of sine is cos. And then obviously, when we said the derivative of sine of x, we just have cos of x as the answer. But in reality, there was also the 1, which was the derivative of that x. So in general, if it was the derivative of hyperbolic sine of f at x, we would still have that cos of f at x, but also we also need to have the derivative of the of f at x, which is, it needs to be attached as well. And then the derivative of cos, we know when we are dealing with cos of x, we ended up with sine of x. So the derivative of cos of f at x, it will be f prime of x times sine of f at x. If we want the derivative of y is equal to hyperbolic tangent of x, we are simply going to use the product rule, because we express the hyperbolic tangent of x as hyperbolic sine over hyperbolic cos. And then if we use the quotient rule, it will be the derivative of the first, which we already know now, is cosh multiplied by the second minus the first multiplied by the derivative of the second, and the derivative of cosh is shine. I think that is one thing, one difference that you need to be able to see here. Normally, when we differentiate cosine um, as part of the normal trigonometric function, we know that its derivative is negative sign. But when it comes to the hyperbolics, it is not negative. The derivative of cosine is still sine. And then from there, it will be the first times the derivative of the second, which is sine. And then it will be cos squared minus sine squared. But then we have already mentioned that this thing is going to be 1 because it corresponds to cos squared plus sine squared, and sine squared, and the plus sine squared involves the product of two signs. That's why the sign is going to change here. And then ultimately it will be the hyperbolic secant squared x. So in other words, the derivative of hyperbolic tangent, it will be secant squared f at x times the derivative of f at x. And we can do the same exercise of using the quotient rule to identify the derivative of hyperbolic cotangent, and you'll find that it will be minus cosecant squared f at x multiplied by this. And then again, the derivative of hyperbolic secant. Remember that hyperbolic secant is 1 over cosh. Then you can still use the quotient rule, and you'll find that the derivative of secant f at x, it will be secant tan multiplied by f prime of x. It's a mistake here. It's supposed to be f prime of x multiplied by secant f at x, and then tangent f at x. And then in the same manner, the derivative of cosecant of f at x. Cosecant is 1 over sine. And then if you use again the quotient rule, you'll find that the derivative of cosecant, it will be cosecant cos, and then but it will be, there is going to be a negative in front of it. So you need to be aware of the negative in front of this this hyperbolic functions. An example: if we want dy dx, given that y is equal to cos of sine of negative sign, arc sine of x, then dy dx is going to be the derivative of cos is sine, as we have already said, and it will be sine of the same expression, arc sine. And then, but then you multiply by the derivative of what is inside here. And the derivative of arc sine is 1 over the square root of 1 minus x squared. That is the section that we were dealing with last. Another example. If you are given that y is equal to x to the exponent cos of 4x, then you need to use the logarithmic law in order to bring that thing down, so that you are going to say ln of y will be equal to ln of this. But because of you can then take this exponent down, it should be cos of 4x ln of x. And then from there, if you want the derivative on the left hand side, because you are differentiating with respect to x, but you are differentiating a function that is described in terms of y, there's always going to be that dy dx component. So it will, the derivative of the left hand side will be 1 over y dy dx. On the right, you are going to use the product rule. The derivative of cosh of 4x, it will be 4 sine of 4x. So it will be the derivative of the first times the second, which is ln of x, plus the first, you write it as it is, multiplied by the derivative of the second. And then so that now if you make the y dx the subset of the formula, it will be y into all of that. But y itself we know is equal to, so this will be your final answer. It does not matter even if you leave it just at y. Right. And then
Sir,
another example, unless
sir,
if there is something that, yes.
yes, I just want to go back to the example that you were doing.
Okay.
So I just want to know when do we apply the lin? Is like when maybe let's say we have the same function. If it's a trig function, is a function to the power function. Do we still use the logarithmic solution?
Yes, because otherwise we know that under normal condition we can find the derivative of x to the exponent n, you see. So where n is usually a constant, that way we say it is n x to the exponent n minus 1. But if the exponent itself is it consists of a variable, then
Yeah.
the only way by which you can be able to handle it you is to simply take it down, and you can only do that by the introduction of the log or the ln.
Okay. Thank you very much. Well, that was clear, sir.
Thank you, sir. Okay. Um, Another example. Remember that so far we have said the derivative of sine is cosh times f prime. The derivative of cosh is f prime times sine. The derivative of tangent is f prime times secant squared. The derivative, and then we also know from the previous exercise when we were dealing with inverse trigonometric ratios that the derivative of arc sine is of f at x is going to be f prime of x over the square root of 1 minus f at x. So if we want to use it in these examples, and y is equal to sine of arc secant 1 over this. Now we have already done this one, that when we talk about arc secant of 1 over this, it will be the same as arc cos of root x. It is part of what we were dealing with in the previous lessons. So we first simplify this, and then from there now, the derivative, it will be the derivative of sine, which is cosh. And it will be cosh of the same expression that followed sine. That one is important for you to know. And then again, multiply by the derivative of what is inside. And the derivative of what is inside, it is going to, in the denominator, we had 1 minus and then square root of x all squared. And then on top, because now we were dealing with the inverse trigonometric ratios, on top will be the derivative of what you are squaring. Now what you are squaring in this case is root x. And then the x, remember, it is the same as x to the power half. So it would be half times x to the power negative half. And negative half is what causes that x to come here in the denominator. And then that is why we know that this part here is going to be the derivative of this one. But then we know again that when we were dealing with the inverse trigonometric function, we said when you want the derivative of arc cos, there is a negative that is going to come in front of it. That's why we have it here, and then you can then simplify this expression. Another example, if we have y is equal to arc tangent 3 to the exponent 2x. Then if we want the derivative of arctangent, remember now we are here. The derivative, not arctangent, the derivative of hyperbolic tangent. I'm sorry about that, because arctangent is the one that involves the inverse. Now, the derivative of the hyperbolic tangent is secant squared multiplied by the derivative here. So that's why I have secant squared of the same thing, and then multiply by the derivative of what is inside. Now the derivative of what is inside, it will be 3 to the exponent 2x ln 3 multiplied by the derivative of the exponent, which is 2. And then you can then simplify this to get this answer. Another example. If you have y is equal to arcsine, and then inside you have cosecant ln of x, then you need to go back to one of the previous lessons, where we know that for arcsine there's going to be the square root of the square root sign, and then 1 minus, and then what follows is what you are going to square, and then on top you must have the derivative of what you have squared, and the derivative of cosecant we are now where, and the derivative of cosecant is actually going to be cosecant cos of the same thing, and then times the derivative again of what is inside, which is 1 over x. And then you can simplify this. You can simplify this, and in simplifying, there's going to be that x here. I think I forgot that x. There needs to be an x in the denominator. I don't know if there's any further question. Right. Now, inverse hyperbolic functions and their derivatives. The procedure is going to be very similar when handling the inverse hyperbolic function as what we did when we were dealing with inverse trigonometric ratios, right? But before we continue, remember that the hyperbolic function, it's something that is it is described in terms of exponents, you know. Like for instance, hyperbolic sine is half into e to the exponent x minus e to the exponent minus x. Hyperbolic cosine is half into e to the exponent x plus e to the exponent minus x. Hyperbolic tangent is e to the exponent x minus e to the exponent minus x divided by e to the exponent. So in other words, all of these hyperbolic functions, they are described in terms of exponents. So we should expect that their inverses somehow they would be defined in terms of the logarithms. To give an example, let's suppose that we want to look at the definition of inverse hyperbolic sine. If you allow y to be equal to inverse hyperbolic sine, then what it means is that hyperbolic sine, what it means is that hyperbolic sine of y is going to be equal to x. That is in a similar way as what we did with trigonometric ratios. But then we know that hyperbolic sine of y is going to be half into e to the exponent y minus e to the exponent negative y, and it will then be equated to x. And then if you divide across by e to the exponent negative y, you are going to get e to the exponent 2y minus 1 will be equal to, and you take this half to the other side, it will then become 2x, and then e to the exponent y. And then in other words, if you simplify this, it will be e to the exponent 2y minus 2x e to the exponent y minus 1 is equal to 0. So this is a quadratic equation where if you allow z to be equal to e to the exponent y, it's going to be like z squared minus 2xz minus 1 is equal to 0. And if you use the quadratic equation, z will be equal to 2x for b squared. Your b is 2x. So, it's negative 2x. So it will be 2x plus or minus the square root of b squared minus 4ac. B squared will be 4x squared minus 4ac, it will be minus 4 times 1 times negative 1. And that will be plus 4. So in other words, and then if you divide everything by 2 in the denominator, because this square root of 4, you can take it out as 2. And then you'll then be left with x being equal to plus or minus this. In other words, and then, but by z, you mean e to the exponent y. So that now e to the exponent y will be equal to this. And then if you introduce ln on both sides, ln of e to the exponent y is y. And then it will be the same as ln of this expression. So in other words, if y is equal to inverse hyperbolic sine, y ends up being ln of this. Now, again, if we were to use the very same thing, and I advise you, whenever we give examples, please do the other exercises on your own. Like, for instance, to show that you can follow the same procedure as what we did for inverse hyperbolic sine, for inverse hyperbolic cosine. The procedure is exactly going to be the same. And you'll find that inverse hyperbolic cosine, it will be ln of this, and then hyperbolic, the inverse hyperbolic tangent, it will be equal to this. You can do these exercises on your own. So what does it mean? What it means is that when it comes to hyperbolic functions, or inverse hyperbolic functions, the main difference is that with the inverse trigonometric ratios, is that in the case of trigonometric ratios, we had functions and angles. But in the case of inverse hyperbolic functions, we do not have angles and functions, because when we talk about hyperbolics, we talk about things that are described in terms of exponent e. And when we talk about the inverse, we talk about things that involve ln. So there is no angle involved there. So what does it mean? What it means is that when you evaluate the hyperbolic function, it does not matter whether your calculator is going to be in the radian mode or in the integer mode. You are always going to get the same answer. Let's take an example of what we started with. When we're evaluating, let's say, cos of 0, it does not matter whether your calculator is going to be in degree mode or radian mode. You are always going to get the same answer. Even when you wanted the sine of 0.5, it does not matter whether your calculator is in a degree mode or in a radian mode. You are always going to get the same answer. So that's one of the main difference between the hyperbolics and their inverses, and the trigonometrics and their inverses. So let me see. Right.